All righty, this is a 67, couple 70s, and a couple 80s. Again, when it comes to these questions, we are always looking just simply about what can you do? And since your variable is in the exponent, you know immediately that you're going to be using logs or natural logs or something in order to get that variable out of the exponent. So step number one is to take the natural log of both sides. And then that's going to force this m minus 7, because it's an exponent, to the outside here. And again, you ask yourself, what can you do? We're going to try to get m by itself. So we're just going to do the next obvious thing, which is I'm going to distribute this. So I'm going to have m times natural log 8 minus 7 times natural log 8 equals ln 92. Again, trying to get the variable by itself. So I'm going to add this entire thing to the other side. So we have our variable and ln 8, ln 92 plus 7 times ln 8. And then the last thing I need to get rid of, or in order to isolate, is natural log 8. So natural log 8. I'm going to divide out to each individual term. All right, so I'm giving you what's called the exact form. And if you need the decimal form, you just get your TI-84 out. So our variable m, the exact form here, this cancels. So 7 plus natural log 92 divided by natural log 8. And once again, you can get out your own TI-84 and get the decimal version if you need it. All righty, 68. Again, the starting point is not what should I do, but what can I do? And it's very easy to tell that this 16 and that this 64 is exponentially related. They're both exponential multiples of 4. So I'm going to get them in that form. So this is going to be 4 squared and then 3x. And this is going to be 4 times 4 times 4 gets you 64. So that's going to be 4 cubed and negative 3x. Now that your bases are the same, you can do this. 2 times 3, 6x, negative 9x. Now, you should be able to see it from here that the only way to make this a true statement is x equals 0. But if you need to take it one more step, so we're going to plus 9x cancels. We got 0 on this side, 15x over there, and of course, divide by 15, and x still equals 0. All right, number 70. So once again, the goal is to get those exponents out of the exponents. So we're going to use the natural logs to do that. So to get that x out and that x minus 3 out, we are going to do x, natural log 2, and x minus 3. Technically, that's a single entity, natural log 3. And again, you just keep asking yourself, what else can I do? That's really obvious. And there's parentheses here, so we can distribute. So I have x natural log 2 equals x natural log 3 minus 3 natural log 3. You ask yourself, again, we're trying to solve for x, so you want to get x to one side. So I'm going to minus this, both sides. And we have x natural log 2 minus x ln 3 equals negative 3 ln 3. Trying to get x by itself. So we're going to pull out x, backwards distributive, or undistribute, however you want to call that, ln 2 minus ln natural log 3 equals negative 3 natural log 3. Divide this single entity out. Just bring that negative before, so I have 3 natural log 3 over natural log 2 minus natural log 3. And again, this is the exact form. So if you want the decimal version, you just get out your TI-84, and I would, when you do fractions in a TI-84, I would do this top part and get the decimal, and then get the bottom part and get the decimal. Do that in 2 separate steps. And then finally, the last step, divide it out and make sure you don't drop that negative sign. All right, number 73. Number 73. Again, you guys just ask yourself, you got to find a way to get that exponent out. So we're going to do that by using natural logs. So I'm going to go ln e x minus 2 natural log 11. Now, here is a little bit of a trick, make it a lot easier. Technically, this is log e of e, x minus 2. Actually, that's going to come on the other side now, right? Goes this way, x minus 2 parentheses equals ln 11. And we know the log of e to 2e is a big fat 1. X minus 2, times 1 equals ln 11. You don't need to distribute the 1. I think you could see that. We're simply going to add 2 both sides. So x equals the natural log of 11 plus 2. Once again, get out your calculator if you need something other than the exact form. It says here for number 79, initial deposit of $4,000 is made in a savings account for which the interest is compounded continuously. That's important. The balance will triple in 15 years. What is the annual rate of interest for this account? Okay, so this particular equation is used specifically for continuously compounded. So be careful you don't use it for things like compounded quarterly or compounded monthly. It's continuously compounded. So that's this equation. So let's pick our pieces of information here. It says our final amount, which is A, is going to be triple of the original. So our original is $4,000. So 3 times $4,000. And then our original principal is the $4,000. That's what we start with. And we have E, and our rate is what we do not know, annual interest rate. So that's R. But we do have a time factor, and our time factor is 15 years. All right. Once you plug it in, the goal is to get that r by itself. So we're solving just like normally. The first thing I'm going to do is the real simple simplification. I'm going to divide out the 4,000. 3 equals E R 15. Again, we want to get the exponents out of the exponents. So we're going to use natural logs here. So ln, natural log of 3 equals R 15. So your rate is going to be the natural log of 3 divided by 15. Now, because it wants the actual percentage and not the exact form, this would be considered exact. So if you were asked for the exact, that's where you would stop. But obviously, since we're dealing with a percent, we want a decimal. So we get out our calculator here. And we're going to do the natural log of 3. And we are dividing by 15. 0.073. So, of course, as a percent, you just bunny hop that percent over, and you have 7.3%, which is pretty good compounded interest. Okay. Number 80 here says you deposit 2,500 into an account that pays 3.5 annual interest rate compounded daily. How long will it take for the balance to reach 3,000? All right, you deposit 2,500 into an account that pays 3.5 annual interest rate compounded daily. How long will you take for the balance to reach 3,000? When it says compounded daily, that's also a clue. That kind of means continuously as well. All right, so you're just going to use the same equation as before. And it says right here, we want the balance to reach 3,000. So 3,000 is our final amount. Our principal that we're starting with is 2,500. And here we have E, our rate. We have it 3.5%, so change it to a decimal. And our time is what we do not know, so T for time. So always start with what you can do right off the bat. You can see we can divide out these zeros, so goodbye zeros. And we have 30 and 25. I can easily reduce that by 5. 5 goes in here 6 times, and 5 goes in here 5 times. There we go. Just kind of keep hacking away at it. E 0.035, and T is your unknown. Once again, we are trying to get that variable by itself, so I'm going to divide out 5. I have 6 over 5 equals E to the 0.035 times my time factor. To get the exponent out of the exponent, we're going to take the natural log of both sides. So that gives us the ln 6 over 5 equals, that eliminates this, 0.035 times that unknown t. Okay, so t is going to equal this quantity right here. And at this point, you grab your calculator. That's natural log 6/5. So it's actually easier to do on a TI-84. So try it on the TI-84. Hit pause the video and do it on your TI-84 and then restart, see if we match. Okay. We are going to 6 divided by 5. So we're going to do that first. 6 divided by 5. There is 1.2 natural log of that divided by 0.035. We get approximately 5.2 years. 5.2 years. Now, just in case we want it in months, of course, that's going to be 2 over 10 equals x over 12, because we want to get it into months if you want. And so we have 24 equals 10x divided by 10 divided by 10. And we are going to get 2.4 months. So 5 years and 2.4 months.